Well, it's a pleasure to welcome Martin back to Princeton. You don't know, he's a veteran of Princeton. He'll be telling us about the M-theory 3 form and ADE gauge symmetry. Take Martin to dinner, right? If anybody is interested, please send me an email right after the talk so that I can make a reservation.
Okay, thank you very much for the opportunity to be able to give a talk. Yeah, it's very nice to see all these familiar faces again. So I want to talk about the M-theory 3 form and its relation to enhanced ADE gauge symmetries. This is based on a paper, mostly based on a paper that I put out recently with Ron Donaghy from early October. There's some related papers and unpublished work that I did with Ron on this topic. And there's also some related work by Marsano et al. And Colanucci et al., but I will not have time to talk about the possible tentative connection with their papers. So as I said, it's about enhanced ADE gauge symmetry and M-theory compactifications. So let's first just start to remember what the original story was. So we have so back in the 90s there were several disconnected string theories. There was the heterotic string, there was type 2. And people started realizing that the string theories are really effective once you start compactifying them. In particular, there's the heterotic string, which you can compactify on T4, and there's the type 2 string, which is compactified on K3. And these theories look in many ways very similar. They turn out to have the same moduli space, same low energy gauge symmetry, generic points in the moduli space. Various arguments were made that these theories should be dual. If you believe in this duality, the heterotic string, of course, has in 10 dimensions has a large non-abelian gauge group, E8 plus E8 or spin-32 mod C2. And if you go to a special point in moduli space where you turn off the Wilson lens, you can recover that non-abelian enhanced gauge symmetry in the low energy theory. So if this duality is correct, that means that on the type 2A side, there should also be some way for non-abelian enhanced ADE gauge symmetry to arise at certain points in the moduli space. But in the type 2 theory, that seems much more mysterious because in type 2, you did not have gauge fields in 10 dimensions. You had Ramon forms, Ramon fluxes, and whose compactifications give you the various U1 factors. But somehow we should be able to see enhanced ADE gauge symmetry at certain points in moduli space if this duality is correct. And the famous paper of Wittens looked at this in detail and found that the points on heterotic side, tuning the moduli to get enhanced ADE gauge symmetry. On the type 2 side, it corresponds to tuning the moduli is that the K3 servers develops ADE singularity, corresponding ADE type, ADE singularities type that corresponds to that enhanced gauge symmetry as you'd expect. So that opens up the possibility, because the K3 is singular, it opens up the possibility that there's something interesting going on there. But you still have to explain what that is. And so where do these non-abelian gauge fields come from? So the story, the idea is essentially following. You can take this ADE singularity and you can blow it up. You can resolve it until you have a completely non-singular space, which is a standard procedure for resolving singularities in algebraic geometry. And the singularities, famously, when you blow them up, there's something very interesting that happens. You find a bunch of exceptional two spheres. And these two spheres, once you completely resolve the singularity, they have a certain intersection matrix. The intersection matrix of these two spheres inside the resolved K3 is exactly inside. It's exactly the Cartan matrix of the ADE corresponding ADE Dinkin diagram. In fact, that's why these things are called ADE singularities. Okay. So that suggests some relation with the algebras, ADE Lie algebras, but precise mechanism is not one that mathematicians at least have seen before. The way it works in string theory is that you, apart from usual supergravity fields, Ramon fields, symmetric, and so forth, you also have certain extended objects, and they were called Ramon black holes, excuse me, at that time. The ones who are interested in the black hole, these Ramon black holes have two spatial dimensions and one time dimension. And so Strominger, I mean, he was doing this in a slightly different context. He was doing the conifold, but essentially the same idea work here. You take the soliton and you wrap its two spatial dimensions around its two spheres, and when you do that, you get a particle in the uncompactified dimensions. Basically, you get one particle for every sphere that you wrap. It's not entirely correct. You need to take linear combinations so that the soliton section is -2. Basically, the fundamental roots correspond to these two spheres. So you get particles in and they transform because of these properties from the intersections. They transform just like you would hope for. They have the right transformation properties to be identified with the missing non-abelian, non-Cartan ADE gauge fields in the uncompactified dimensions. Now, as it stands, those particles are massive because when you wrap the brane, the mass of the particle that you get in uncompactified space-time is proportional to the area, proportional to the volume of the two-sphere that you've blown up. But these things are half BPS, and the relation between the area and the mass is protected. So when you shrink the area to 0, these particles become massless. So precisely when you shrink all these two spheres down to a singularity, precisely at that point, do these particles become massless, and do you see an ordinary massless gauge field. Okay. So very standard story, but just wanted to review it. Now, of course, we didn't have non-abelian gauge symmetry in type 2 before, so this opened up new possibilities. But it wasn't the only way to get non-abelian gauge symmetry in type 2. In type 2, it was soon after realized that the Ramon black holes are actually d-branes. Another way to get a non-abelian gauge symmetry is just take d-branes, forget about the singularities, just take the d-branes and stack them on top of each other. But there are certain ways of lifting it where this mechanism of creating non-abelian gauge with singularities is more important. Namely, if you take the type 2 heterotic duality, well, there's a modulus space, and you can start decompactifying some of the circles of the T4 to go up in dimension, which corresponds to, so the first time you do that, you go from heterotic on T4 to heterotic on T3. On the type 2 side, you just open up the M-theory circle. Now we're talking about M-theory on the K3 surface with the singularity. And you could go even further. It turns out there's another circle that you can decompactify by taking M-theory on elliptic K3 surface and taking a certain limit of it. And certainly in the M-theory and the F-theory contexts, there aren't really any d-branes. There's only M2 and M5 branes. So if you want non-abelian gauge symmetry in very high dimension, you have to do it with these singularities. You can't do it from branes. Particularly model building that's done standard model-like constructors or gut model-like constructors, F-theory or M-theory, you need gauge symmetry in high dimensions or you won't get chiral matter. So that's why model building on G2 holonomy manifolds, F-theory on Calabi 4 manifolds, the gauge symmetries always come from singularities, come from branes. Okay. So can't just forget about them. Now, of course, this picture of N2 branes of vanished types has in many ways been very successful. Nevertheless, there's some issues which have started to appear over the years. And when I say issues, I don't mean to say that there's anything wrong, that the M2 brane picture is wrong, really. I'm certainly not saying that. Before it's successful for that. But there are some ways in which it's incomplete. There are certain things certain vacuum, certain phenomena that you can fairly easily see in dual pictures, but that you somehow cannot see in this picture of vanishing cycles with N2 branes wrapped on them.
Does cannot see mean that there's some strong coupling involved in symmetry?
Not sure how to phrase it that way. The way to phrase it, I think, is that I mean, there are multiple issues, but I think the way I'd phrase it is that the picture we rely on is that we want to wrap N2 branes on these resolved cycles. and that picture is accurate, is really correct in the limit in which these cycles are very large. And then you use BPSness to extrapolate to the situation where these cycles are very small. Now, basically, it turns out that when you just in the limit where they become small, there are additional branches that can open up. You didn't see from this picture. Basically, branches where the M2 branes can condense in a certain sense. And you'll never see that in this picture where you have M2 branes wrapped on large volume cycles because they're extremely massive there. They're much more massive than any supergravity. There's no way they're going to condense in that picture. The phenomena where these things condense, and you can't get it from this M2 brane picture. That's sort of the intuition. Okay, so and I'll discuss some examples of that later. And so also a closer look at some of at the duality suggests that there's maybe another way of thinking about this problem of enhanced gauge symmetry. So that's what I want to talk about today. One of the strongest hints, I think, certainly the thing that I'll be using, is a paper by Friedman and Morgan that appeared in 2000. It's 23 years ago at this point. So they wrote a very interesting paper that essentially, I mean, I'm not sure to exactly phrase that way, but essentially it contains another way to see how the enhanced gauge symmetry at the ADE singularity appears. But they had a certain mathematical way of thinking about it, and it doesn't quite seem to line up with the physical way of thinking about it. So we have to somehow connect the two. But for the moment, I just want to talk about what Friedman and Morgan said. So Friedman and Morgan, incidentally, were studying F-theory heterorhotic duality, and they were trying to understand some aspects of F-theory heterorhotic duality, and that's where this came up. Friedman and Morgan essentially said the following. Suppose that I compactify on a rational surface, I think M-theory or F-theory, and I compactify it on a rational surface whose Picard lattice contains an ADE root lattice. And Picard lattice is the lattice, the line bundles, the possible line bundles that you can put on that surface. Yeah,
I'm confused about your earlier statement. Yeah. You had this picture that works well with type 2, but does not work well with M-theory.
I would say it doesn't entirely work in type 2.
I don't see the difference between them because you had a theory in 6 dimensions.
Yeah.
If you compactify with another circle, you go to 5 dimensions. Yes. Everything is still weakly coupled. And then there isn't really a difference between the two, between the type 2A and the M theory.
Yeah, so the branch I want to talk about, you don't see either in the 2A description or in the...
Okay, so the 2A description and the M theory description are equally bad.
Yeah.
Thank you.
So they said take a rational surface whose Picard lattice contains an ADE root lattice. So the Picard lattice is just a set of line bundles that you can put on that space. And they wrote a very interesting bundle on the surface. So the fibers of this bundle are just the ADE, the corresponding ADE Lie algebra itself. Okay. And what they did is for every Chern generator, they just took a trivial line bundle. And for every non-Chern generator associated to a root alpha, they take the line bundle O of alpha. Since the root lattice is the ADE lattice, that's the line bundle I can take. Okay? So the fibers, if I sum this all up, the fiber is, as a vector space is just the Lie algebra itself. And in fact, this bundle has a Lie algebra structure. It's non-trivial. It's not just the sum of trivial line bundles. It is, however, reducible. It is completely reducible, which means that the structure group is not the full non-abelian ADE Lie group. The structure group is just a Chern. It's just the maximal torus inside the ADE Lie group. But we can take that bundle and put that on our surface. And now we're going to do a Kaluza-Klein expansion, very similar to the way you would do in heterodic string. Okay, so how do we do it in a heterodic string? Well, you take your gauge field and okay, so now you expand it in 0 forms and 1 forms on the internal space. If you're interested in the 0 modes, you take certain harmonic modes, which are counted by the bulk homology groups of the bundle. Okay? So if for every the bulk homology group of degree 0, I get a gauge field in uncompactified space-time dimensions, and for every the bulk homology group of degree 1, you get an adjoint field. In fact, we've written the complex adjoint field in the uncompactified space-time dimension. And so now the low energy effect, the gauge fields and adjoint fields that you're going to see in the low energy effective theory just amount to computing these bulk homology groups. And I realized that I've not written this in the most optimal way, perhaps, but anyway, the claim is that at the generic point in the modular space, the only bulk homology you see, that is the only massless modes that you're going to see, come from A0 of these trivial line bundles here. That gives you R factors, so roughly you think of that as being the U1 to the R that you were hoping to expect.
Excuse me,
and
what is W sub adjoint? I have a question. What is W sub adjoint? Is that the same as W?
Same as W. W sub adjoint is the same as W. Yeah. Yeah, it's the same. And so the claim is that at the generic point in modular space, that the bulk homology groups of these additional line bundles here are all 0. They don't contribute anything, except when you develop a singularity. So the claim is that if you develop a singularity, then, well, actually, mathematically, what you resolve it, and you compute the bulk homology groups in the resolution, and then it turns out that you basically get one generator for every positive root in the algebra. Precisely the claim, some algebraic terminology, algebraic geometry terminology, but the claim is that these bulk homology groups are non-zero and one-dimensional, in fact, precisely when there is an effective curve in the class alpha. So alpha is some homology class, some corresponds to some divisor. Divisor is a linear combination of algebraic cycles. If it's a positive linear combination of algebraic cycles, that's called effective. And precisely when there exists a positive linear combination, then the bulk homology groups are non-zero, and otherwise they're 0. So as a simple example, if you take this the ordinary A1 ALE space, so generically, it looks like xy plus z squared is equal to mu. Okay, so I've deformed the singularity here by turning on some complex structure deformation u. This you can think of this. You can think of this as a piece of a quadric. You can compactify this to a quadric, which is P1 plus P1. Two rulings, line L1 and L2. And there's one linear combination of that, which doesn't intersect infinity, which is the combination of course L1 minus L2. So now I've written, there you go. I see I went in the wrong direction. I've written alpha as a linear combination of two algebraic cycles, but one of them has a minus sign, so this is not an effective cycle. Okay. Now there's only one complex structure modulus here, it's mu. Okay, so now let me two mu such that you go to singular points. So I set mu equal to 0. Okay, now I have a singularity which I can resolve and blow it up. When I blow it up, I get an exceptional P1 in the class alpha. At that point, I have an effective curve, namely the exceptional curve. And I'm going to get non-zero homology here at that point. And so in the low energy theory, you're going to see extra gauge fields and extra adjoint fields, precisely corresponding to the positive roots of the algebra. The negative roots are basically the complex consequences of those. Much like the story of rat and two brains, where you wrap a brain, you wrap it into a brain. Okay, so yeah, again, essentially, I just said this, but precisely when there's an effective curve with the class alpha, you find that these homology groups are non-zero and one-dimensional. And a non-zero generator for H0 means a massless gauge field, and this is a Klein expansion. And a generator of degree 1 means you get a complex adjoint field. If we take this surface if we take the surface with this deformed and linear singularity and put this particular bundle on it and just do an ordinary closed line expansion on it, precisely at the right point in the moduli space where you expect non-abelian gauge fields to appear, precisely at that point, from this point of view, you do see extra non-abelian gauge fields appear. Okay.
Did you use a U1 gauge field here? Or what was the?
Yeah, we already had those. We already had those.
So you used an abelian gauge field.
Yeah, so we already had the U1s. We always have those. The point is that these the cohomology, right? The cohomology of these is pretty simple to compute because it's completely reducible to this cohomology of Lambo. So the point is that this normally, right, a non-Cartan piece is normally this contribution is moduli dependent. And you only get a non-zero contribution precisely when you tune the complex structure moduli to get a similarity. So I spent like 5 minutes explaining this or something like that. The proof is only like 2 or 3 lines. It's really not that complicated. Yeah, that's the fundamental thing. Well, one of the fundamental things that they pointed out. So it's a very nice way. It's a very nice way for to see that you can get enhanced gauge symmetry, but it doesn't. You know, there's a slight mismatch because you know, if we start with M theory, and I'm going to think mostly in terms of M theory, F theory. Start with M theory, right? The fields in the theory, they don't contain any propagating gauge fields. We don't start with a bundle in 11 dimensions or 12 dimensions or whatever it is that you're looking at. And we have in M theory, you have a free-form tensor field. In F theory, there's also a version of a free-form tensor field. There's no gauge fields. But Friedman Morgan said, if you allow me to start with this gauge field in higher dimensions, and I take this particular bundle, and I just do an ordinary closed line expansion, precisely when you expect to get enhanced gauge symmetry, you do get enhanced gauge symmetry. So it's simple in that sense because you start with bundles and gauge transformations, and at some level it's simple. I don't have to add extra objects to the theory except this bundle. And yeah, I'd say that if you ask the mathematician to explain enhanced gauge symmetry in heterotic type 2 duality or heterotic M theory duality, this is what they would and eventually did come up with.
When you get enhanced gauge symmetry this way, is it localized at the singularity?
That depends on the I'd say that depends on the context that you.
But if I naively took your construction, the answer might be no.
Yeah, and I think actually it shouldn't. We can talk about that, but in a situation where you have both a boundary in sort of the F theory heterotic duality setup, where you have both some kind of boundary and a singularity, there's 2 ways to see the enhanced gauge symmetry appearing. One is by the heterotic theory which lives on the boundary, and the other is by you know, whatever happens at the singularity. And those degrees of freedom shouldn't be independent. See, and that's basically what happens. These modes that you have here, they're not really localized to the singularity. They stretch out all the way to the boundary, and they actually give you the bulk homology groups on the boundary, which we call the heterotic theory, that are normally responsible for enhanced gauge symmetry in the heterotic string. So it shouldn't be disconnected in that context, certainly. Otherwise, you'd have a puzzle. I would have, it looks like I double the degrees of freedom. Okay, so yeah, so it's a very nice explanation, but it doesn't quite match up with the physics. So we want a physical explanation for this. So that's what I'm hoping to do today. Now, I should also immediately put out a disclaimer that I will be trying to talk about spacing with singularities, and we don't have really a good microscopic description of M theory in the presence of singularities. So there's a certain amount, I won't be able to present the derivation, but what I think we'll be able to do is have a sort of plausible picture how this will work. And perhaps more importantly, there are some applications, there are some things that I could do that I couldn't do previously with the rep and two-break picture, which we'll talk about later. Okay, so what's the possible relation between the physical, string theory setup and this Friedman-Morgan observation? There's a hint you get by thinking about the free form. So usually the free form, the way we think about the U1 gauge fields in the compactified theory, I'm going to just mostly restrict the M theory from this point onwards. The U1 gauge fields in if you compactify M theory on an ALE space or K3 surface or whatever it is, the way you get the U1 gauge fields in uncompactified dimensions is by taking the free form and doing a Kaluza-Klein expansion on it, and by expanding it in harmonic forms. And usually we expand it in this way. We take the harmonic forms which are associated to the first Chern class of the line models of alpha I, where alpha I are the fundamental roots. That gives us a particularly nice basis, of course, where this generator corresponds to the co-roots. Now, if I take this bundle which I wrote 2 slides or so ago, and I look at the Chern-Simons form for it, and the Chern-Simons form here, I've just written the expression A wedge F. It's a slightly simplified version of the Chern-Simons form, which I'm allowed to write because the structure group is abelian, so I don't have a full complicated expression. I can just trace A wedge F. The F here is meant to live on the internal space, on the ALE or on the K3 surface or whatever it is. So this is just abelian. And so now this will have an index in the uncompactified space-time. And you just expand this and you get the same expression. Okay. So that suggests that the M-theory form should be thought of as the Chern-Simons form associated with this tautological bundle W adjoint that I wrote a few pages ago, which now by Friedman-Morgan. And I should say incidentally, so Friedman-Morgan wrote the original paper, but there's been a number of follow-up papers by Chen and Lang. Friedman-Morgan were mostly looking at E6, E7, E8, and Chen and Lang discussed all the other cases, all the other A and D cases. So this suggests that you should, the relation between these 2 pictures goes through the Chern-Simons form. I mean, you should think of the free form as the Chern-Simons form of this bundle, this Friedman-Morgan bundle. Okay. Now, the idea that the free form should be related to Chern-Simons form, as been previously suggested, it's come up, I believe the first time it came up was in the paper of Wittens in 96, where certain things were only naturally understood if you took the free form to be valued in the topological part of the free form to be associated with the Chern-Simons form associated with bundle E8. But of course, there are some obvious issues if you're to take it literally. Starters, as I've said several times now, there are no propagating fields in M theory. So you can introduce a bundle, but you have to do it in a way that you don't introduce propagating gauge fields. The most evolved model that I think I'm aware of that was written down in a nice paper by Diaconescu, Fried and Moore back in 2003. So they gave a specific model for the free form along these lines. And they said the following. So for us, they said the free form is not just a free form tensor field. For us, the free form is a pair, what we call the little free form, so ordinary free form tensor field in some sense, as well as a connection on a bundle. Yeah? And for them, because they wanted to make context, well, for them, the bundle was E8. And now that data, it has a curvature, and the curvature is recovered as follows. It's D of C3 plus trace average F minus a half trace R H R. So the idea being that the topological part of the four-form flux is captured by the bundle plus a half integer shift correction, and not by this piece of the free form. Right? The topological part comes from the bundle. Now, so it's fine to introduce an additional gauge field, but we do want to, in an ordinary setting, we do want to course, recover the usual degrees of freedom associated with free form. So when you introduce additional field, you also have to introduce some extra gauge transformations in order to recover the usual gauge equivalence classes of the free form. The gauge symmetries that they had, so they had the usual two-form symmetry of a free form, but because they added this extra gauge field, they also had to introduce a one-form symmetry to kill the degrees of freedom associated with the gauge field. So psi here is just literally a Lie algebra valued, it is in the same space. It's Lie algebra valued one form, arbitrary Lie algebra valued one form, which shifts the connection, which is sort of just arbitrary shift of the connection, and then it has a sort of twisted term over here. Yeah. So this one form symmetry is literally a Lie algebra valued one form. It kills all the degrees of freedom of the bundle, so you don't get any propagating gauge fields.
Sorry, don't you need a D in front of omega or not?
Yeah, so in the way I've written it here, I didn't want to write it out, but omega here is closed to integral periods. So it has two pieces. It has a discrete piece, which is harmonic integer quantized, and then it has a continuous piece, which is D of a two form. So that's the usual. Yeah,
but the terminology that is a two-form gauge symmetry.
I mean, its continuous part is its continuous part.
And below that, there's a one-form gauge symmetry psi.
Yeah.
Are you using the same terminology or is it different thing?
If I ignore, so if I take the let me put it this way, if I throw away the harmonic piece here, it's the same. So you think of this as D of, I don't know, I need another letter. D of lambda, okay, where lambda is arbitrary two form, and this is, excuse me.
You can describe it by saying that omega is required to be closed.
Yeah, closed in integer periods.
Oh, okay.
Yeah.
Omega is like a three form in size.
It's a free form, but
it's size like a one form.
Yeah.
Interval 2 and 1.
I should write. I should, for simplicity, I should just ignore the harmonic piece of omega. Then I could just have written D of two form. The continuous part of the symmetry is parameterized by a U1 valued two form. And then there's a discrete feature for the large case transformations.
Well, I have a comment. I mean, maybe you're going to say this, but I mean, if the manifold has boundary, depending on how you define boundary conditions, there are propagating gauge fields. Maybe this is your...
Yeah, absolutely. Okay. Yes. Very important. Thank you.
What is the Chern-Simons action with two entries?
Yeah, so it's with two entries. Yeah, so so I have a path. I have a parameter next to parameter t. A path which takes you from A to A plus psi. Okay.
Or multiplying psi by a parameter that goes from 0 to 1.
Yeah.
So you mean the difference of the two Chern-Simons actions? Probably.
Yeah, I mean, and the integration which you have integrated over 3 dimensions integrated over whatever, and then the final dimension integrated over that parameter t. Okay, so yeah, so it's very interesting. So okay, so we've introduced this additional gauge symmetry, but then we also immediately said that, well, it kills all these gauge fields that we just introduced. So how exactly does it help us? And now this gauge symmetry actually it has been previously considered in people studying topological gauge theory. So usually when we talk about Donaldson-Witten theory, the way we tend to think about it is by taking n+2 supersymmetric Mills theory and twisting it to get a topological theory. There's another way of thinking about it, which is introduced by Brooks et al. And by Pauline Singer, which is that you start with an action which is manifestly topological invariant. The action that they took was this trace FHF. And trace FHF has a larger symmetry than just ordinary zero-form gauge symmetry. In fact, this one-form symmetry psi that we were talking about is the additional gauge symmetry that an action trace FHF would have. So their idea is you start with a simple topological action and this sort of enhanced gauge symmetry. In this case, it's the same one-form gauge symmetry, so it's a Lie algebra value 1 form. And that looks manifestly topological. And now what you do is you, I mean, they were interested in studying Donaldson width theory. So what they did is they took this 1 form gauge symmetry and they gauge fixed it, mostly gauge fixed it using instanton equations. And at that point, they when you do that, you have to do some of these, BRST manipulations to level the Lagrangian, introduce extra terms and extra ghosts. And lo and behold, when you do that gauge fixing using the instanton equations, starting with this completely topological theory, you actually end up with something that's essentially the twisted NX2 symmetric Yang-Mills theory. So that's another way of thinking about Donaldson-Whitten theory. In that context, it was already pointed out that when you have a boundary, there's a natural boundary condition that you can write down. In fact, they wanted to cover Chern-Simons theory on the boundary. So you have a manifold and it has a boundary. You naturally want to get Chern-Simons theory on the boundary. And the Chern-Simons theory doesn't have a shift symmetry. And in fact, there's a natural boundary condition that you should impose here, which is that your 1 form symmetry should preserve the bundle of the boundary. They actually wrote in a slightly different form. What they did is they introduced an additional 0 form redundancy, and then they said psi equal to 0, but there was no condition on the 0 form redundancy. But as far as the counting degrees of freedom goes, it's essentially the same idea. So we had a bundle and we had psi, but now we restrict psi on the boundary, this boundary condition, which means that in the bulk, all the degrees of freedom of A get killed by psi. But on the boundary, because I've restricted psi, and A no longer gets killed by this 1 form gauge symmetry. So now on the boundary, you actually get another 1 form. Your A actually survives as a physical form with only an ordinary 0 form gauge symmetry. Okay. The Chern-Simons theory in the boundary describes, in some ways, it's a kind of edge mode. You restrict your gauge transformations, you now get extra fields living on the boundary. DFM said a similar thing. They were considering an 11-dimensional manifold with boundary. And as derived by Hojava and Whitten, on an 11-dimensional manifold with boundary, you expect an E8 vector multiple, Yang-Mills vector multiple living on the boundary. And a DFM picture that essentially arises in this way. There's a boundary condition you have to impose, and that ends up restricting your 1 form gauge transformation to the boundary. Just that on the boundary, you're left over with an actual Yang-Mills vector multiplet. And in fact, we would, in certain contexts, we would identify that with the vector multiplet of an 8 heterodic string, which is, it's a dynamical thing. It certainly doesn't have a 1 form gauge symmetry. So I want to argue that basically that's a very similar thing is happening when you consider other defects. In particular, in my case, I'm interested in singularities. Whenever you have any kind of defect, you should start worrying about the restrictions you have to put on this 1 form gauge symmetry psi. To make our picture look like the one that was considered by Friedman and Morgan, we can actually just do what Brooks et al. And Beaulieu-Singer did. Namely, it's convenient to just do the gauge fixing using instanton equations, because then I can just think about solutions to instanton equations, which on the algebraic surface means you can think about holomorphic bundles, which is what Friedman and Morgan were thinking about. So that's the setup we'll take. We're thinking about holomorphic bundles, and we take, to reproduce the free form I showed you before, you want to take this tautological bundle that Friedman and Morgan considered. And then we just do the Kaluza-Klein expansion, as I wrote before, okay? But now with the following words, so to speak, right? Remember that in the DFM model, any shift in the DFM model, any shift of the gauge field is normally considered a gauge symmetry, right? Because I can always undo it by picking the appropriate psi and just putting it right back. Okay. But the point here is that these particular zero modes that we're interested in, that were discussed by Friedman Morgan, they're not just any old deformations of the gauge field. They're actually special. Namely, they have special behavior along the exceptional locus. So these 0-1 forms corresponds to a deformation of the bundle, and particularly it can restrict to a non-zero deformation of the bundle along the exceptional cycle. The zero forms can be zero as some component and non-other components of the exceptional locus. So these, if you want to think of it as one-form gauge transformations, well, in the limit that, because they have non-trivial behavior over the exceptional locus, the limit that you shrink your cycles back to zero, they're going to be singular one-form gauge transformations, and not smooth one-form gauge transformations. They're going to be singular because they deform these ones. For example, they deform the bundle or sheaf that you get along the singularity. Okay. So therefore, I think it's reasonable to say. So this is the basic proposal. These special deformations which have a non-trivial behavior along the exceptional cycle that would correspond to a singular gauge transformation in the limit, you should not include those in your set of allowed one-form gauge transformations. You should exclude those from your set of allowed one-form gauge transformations. And when you do that, these deformations are no longer killed. Obviously, by definition, these deformations are no longer killed by your one-form gauge symmetry. Never correspond to physical modes. So that's the picture that I have for these things. And I can't, had some questions earlier. I mean, I think this is reasonable. I don't know in what sense I could prove this, but it matches up with a lot of things. It's a very natural condition to impose. It matches with the dualities that I studied. So it's,
if there is an
that choice of gauge.
Sorry.
What motivates that choice of gauge fixing? I mean, that's, of course, the instanton equation is a nice equation, which is non-invariant under shifting by psi. But, what if we chose some other equation?
Yeah. So, there's a certain amount of hand waving that I have to do here. So if I compare this with the what's happening on, if I compare this with what's happening on the heterotic side, it corresponds exactly to throwing with the heterotic string on a T2 or T3. It corresponds exactly to throwing out all the Kaluza-Klein modes. So you truncate to the zero modes. That's what you're interested in. So in this context, I'm not sure I can prove that that's the case, but that's sort of the that's sort of the intuition. By doing this, I concentrate.
Saying that the non-zero modes of the heterotic string are in type 2 heterotic duality dual to the something like the modes of F plus star F, where F is this gauge field that we use to model the C field. Is that right? Yes.
I didn't entirely hear it, but I mean, you could do a Kaluza-Klein expansion, picking some metric and doing some Kaluza-Klein expansions. And at least a subset of those modes, you can just restrict to the boundary in the heterotic F-field duality setting. And those modes on the heterotic side, the modes that I've thrown out here, basically, by doing this gauge fixing, are exactly the Kaluza-Klein modes. And the Kaluza-Klein mode, so on the heterotic side, the only thing I'm left with by doing this gauge fixing is the zero modes, the double cohomology groups, and not any of the massive modes from the compactification on the T2. Yes. Yes.
Go ahead.
Okay, so there's something I don't understand. So previously, when you wrote this equation, delta A equals delta little a, and so on, that A was a connection on a sum of line bundles. So the structure group was U1, but then because your sum of line bundles included a sum over roots, I think you were saying that really it's adjoint valued, but the structure group, as you said yourself, was abelian. It was in the Cartan.
Bundles abelian, yes.
Yeah, right. But now I mean, maybe it's just notation on this page, but in the equation F plus star F equals 0, that F is the field strength of this, let's call it this hidden E8 gauge field in the C field. Okay, the one that becomes
this is something.
Right. But so that's a non-abelian connection. So in the F plus star F equals 0, that's an equation for a non-abelian connection, namely this fake connection that can be shifted by psi. Now, when you write this expansion here, in the next line with delta capital A, is A that fake gauge field that we use to model the C field, or is it a connection on a sum of line bundles with a abelian structure group?
These line bundles in question all have natural ASD connections. The fact related to the tautological, in the ALE case, they're naturally related to these tautological bundles discussed by Kronemer, Nakajima, and other people. So, yeah. This equation says I want ASD. ASD on an algebraic surface means holomorphic and stable. But
it doesn't mean it's a sum of line sum of line bundles.
No, I didn't say that, but there are, on the sum of line bundles, there are solutions to this. I didn't say that this implies that the sum of line bundles. You have to do.
Okay.
I'm just saying that the bundle in question carries. Yeah. So first, the bundle in question carries anti-self-dual Yang-Mills connections, and also, so I mean, I'm a little quicker, but why should I pick this bundle? Well, I want to reproduce the free form, right? I want to reproduce the Kaluza-Klein expansion of the free form. So in fact, if you take that Kaluza-Klein expansion, you see, you actually took a few. Yeah, so yeah, that's not exactly what I want to say. So if you believe that it's a sum of line, I was going to say that, but that doesn't answer your question. If you believe it's a sum of line bundles, you can use this formula to work out which line bundles you have. That's not exactly what your question was, I realize. The question was why am I looking at the sum of line bundles at the first place? Is that correct?
Yeah, that's correct, because in the top equation on this page that you're showing, I was assuming we had a non-abelian structure group.
Yeah, but you want a U1 to the R in the low energy theory.
So it's an ansatz for why the low energy gauge group is U1 to the R.
If you want U1 to the R, so you only want a bundle which in which U1 to the R remains unbroken.
I'm going to postpone my question.
Okay. Okay, yeah, so that's the idea. So you add a bundle with this free form being the Chern-Simons form. You add this gauge transformation psi, and now you impose some natural restriction to get extra modes at the singularity. Now, I've talked here now there are a few things that you'd have to address. One is what gauge group are you going to take? So the event, they used E8. That reasoning is based on, well, I'd say E8 is not quite enough for me. If you can embed the singularity in E8, that's good enough. But the math that I showed you, this tautological bundles and so forth, all that goes through for any ADE singularity, and there's an infinite series of them, so I could make the rank of the gauge group arbitrarily large if I compacted for any theory, the ADE singularity of arbitrarily large rank. What gauge group you take, I'd say E8 in general, I'd say is not enough. This suggests that you should take a larger gauge group than just E8. The other issue here that's not addressed, so we're just talking about some kind of modes from the free form, and free form is a bosonic field. Now, of course, the vector multiplet in 7 or 8 dimensions, it's a super multiplet. It doesn't have bosonic degrees of freedom. It also has spinors, the gauge genome. It's not entirely clear, I would say, how to recover those fermionic modes at this point. I'd say, in fact, there's a similar issue if you think about the way that the 8 vector multiplet in the DFM story arose at the boundary of an 11-dimensional manifold. So you can get the gauge field from this bulk gauge field and restricting the one-form gauge symmetries. But the Yang-Mills multiplet on the boundary also contains fermions, and you still have to add those by hand into the sets. They don't come from some bulk adjoint fermion that we know of. So you would hope that there is, in fact, some kind of bulk adjoint fermion, some form, that would give rise both to the gauginos in 11-dimensional one-form boundary as well as at singularities. But how that exactly would work is, at this point, is not clear. I also want to quickly point out some intriguing similarities with the K-theory description of Roman fields and Roman charges. How am I doing on time, incidentally?
10 more minutes. There were many questions, so you can go ahead.
Again, I don't know exactly what to make of this, but there are certainly a number of intriguing similarities. So in that story, you were considering type 2A now. And in type 2A, we have not just 4-form fluxes, we also have 2-form fluxes, 0-form fluxes of every even degree. And in the K-theory classification, what's done is you express the Roman fluxes in terms of the Chern character of a UN bundle. This time the structure group is not the 8, but it's a UN bundle. And you don't just consider trace F, which F, you also consider trace F, which F, and trace F, and so forth. This was put in an interesting, so there was an interesting paper by Horjava on this, who thought of these gauge fields as arising from unstable design branes. So in Horjava's picture, there's an unstable design brane. It has a gauge field, it has a tachyon, and then it has some adjoint fermions. And from his point of view, by a certain tachyon condensation, you can create T-branes of lower dimension. Horjava points out in this paper that the field content of this unstable D9 brane is very evocative of an 11-dimensional origin. And if you take the tachyon to be the Wilson line around the extra circle, and you combine the two 60-component spinners into a single 32-component spinners in the adjoint of UN, that looks like something that could come from 11 dimensions. So in this story, at least, you would have some kind of bulk 11-dimensional KG. But I would say it's evocative, but it's highly, it's not at all understood what the relation is, if any. Another thing I wanted to point out is that, so I've talked about these topological bundles, and as I've said, the structure group is generic point in modular space, at least they're just one bundles. The same bundles, if you studied the McKay correspondence, then you've seen these line bundles for each of these associated with this T bundle. You've seen those line bundles before. So in the McKay story, there are two ways to get an ADE Dinkin diagram. There's the one we've already talked about. You solve the singularity, you get two spheres, they intersect according to a Dinkin diagram. The other way is you take the irreducible representations of the discrete group gamma in SU2 that you use to model out to get ADE singularity. And there's, for every irreducible representation, you have a node, and there's a way of doing tensor multiplications to arrive at a Dinkin diagram for that, which is the same Dinkin diagram. There's a geometric explanation of this correspondence due to originally Gonzalez, Frumberg, and Verdier. And what they said is to each irreducible representation, I can actually associate a bundle, so called Ri, on the resolution. And the first Chern classes of these bundles, Ri and Rj, is exactly the inverse of the cartel matrix associated with the ADE group. Now, if you if you look at the T bundle, if you actually look at the line bundles that span this T bundle, this topological bundle, for type AN, it's exactly the sum of these Gonzalez, Frumberg, Verdier line bundles. For the type D and E cases, it's almost that. You want to take some of the line bundles, but some of these bundles have higher rank in that case. So for E6, you have the rank 1, rank 2, rank 3 bundle, etc. But the line bundles that show up in the tautological bundle that I talked about are the determinants of these bundles if the rank is larger than 1. That's exactly the same. Bundles show up. Well, at least certainly some of these bundles shows up in this context. The effect that you have to take the determinant is interesting. It suggests that there's a kind of discrete symmetry that you might be able to turn on, and that may be related to this issue of discrete fluxes that you can turn on ADE singularities. Certain discrete fluxes you can turn on ADE singularities, which free certain moduli. Unfortunately, I've tried to think about this. I still don't quite understand it. At this point in the talk, I don't really have time to continue on that point. Okay, so I've tried to advance this alternative explanation for enhanced gauge symmetry at a singularity. Now there's a natural question: why do you care about it? I mean, we already had an explanation. Why should you have another one? Well, there are a few advantages. For one, I resolve the singularity. I strictly don't have to do that. I could work with modules over coordinate ring and compute X groups. It's a principle possible. But I think what more important thing is that there are some, I was alluding to several times before, there are some interesting phenomena that you could see in dual pictures, but you somehow can't see in F theory and M theory picture. So that's what I want to talk about in the next few slides. Perhaps more speculative or aspirational, we've considered two kinds of effects. We've considered boundaries and we've considered singularities. It's probably productive to start thinking about other defects in which you get some form of non-enhanced and enhanced non-abelian gauge symmetry. D-branes will be naturally on that list. And if you can do singularities in D-branes, you should also be able to do D-branes at singularities, maybe even something like ABGM. But that's more aspirational at this point than anything else. Okay, so applications. I think I only have time to really discuss one or two. So here's one. So so at this point of enhanced gauge symmetry, we saw that there were certain scalar fields which were counted by the topology of the line bundle associated with a certain root. As I said before, they correspond to bundle deformations, and it's a bundle deformation that you can literally turn on. Namely, you can make a bundle where this holonomy takes values in that direction. If you turn on a connection with the corresponding, corresponding root, that upper triangular element actually has a non-zero holonomy. When you do that, when you turn on those holonomies, and this is actually what Friedman and Morgan were studying, you don't change the singularity. You just deform the bundle on the singular space or on the resolved singular space. But the space itself does not get deformed. The only thing you're changing is the bundle. Again, so there's this bundle. I've used here the fundamental representation rather than the adjoint representation. If you take it for the simplest case, the A1 singularity, you restrict it to P1. What you get is just the sum of two line bundles. It's O minus 1 plus O1. If you want the adjoint representation, you take the adjoint of that. And this bundle has a deformation to O0 plus O0, in other words, to the trivial rank 2 bundle. And this deformation actually extends to the whole surface if it's a rational surface. In terms of the adjoint field, I've taken this non-Cartan generator, and I've taken, so turning on this H1 in terms of the Lorentz effective theory corresponds to turning on this upper triangular element associated with the root. As I said before, this used to be a problem in the N2 brane picture. In the N2 brane picture, we had enhanced gauge symmetry at the point where you get a singular variety. But here there's another branch that opens up where you can turn on expectation values like this. And you didn't have them in the rep N2 brane picture. Now, it turns out that actually for this simple example, the D terms aren't satisfied in the sense that there's a notion of stability and these things are not stable. But these semi-stable configurations, you really need to have them because if you start compactifying further, there are tons of configurations, which includes semi-stable things. Excuse me, configurations like this, which will be stable. Yes.
Sorry, the terms are not satisfied, and these are why are these vacuum?
Can I answer?
Yeah.
I think he's roughly saying that if you have a six manifold fibered by K3s, then you can obey the D equations, D-term equations in 6 dimensions over not in 4 dimensions.
Yes. I'm not sure I should call them vacua at this level. They're only vacua if I ignore the D terms. So the F terms is the F terms are D terms, it's supersymmetric. And at least in this particular setting, the simplest setting, yeah, it's true. The F terms are satisfied and not the D terms. But as soon as I compactify this ALE and fiber it, I can make configurations where it looks like this and it is stable, and where the D terms are satisfied. And in fact, the typical example that as mentioned before is if you take a rank in the heterodic type, take a rank 2 bundle and a rank 3 bundle, and you take the extension. Certain modular space in certain point in the modular space of Kähler moduli, that's actually going to be stable. But you don't ever see that in this. You don't see those configurations in this picture. Okay, maybe this is the last thing that I'll say then. Yeah, so we are running out of time. This used to aggravate me to no end. Consider F theory compactified on the Calabi-Yau fourfold, or even M theory compactified on the Calabi-Yau fourfold. Becker and Becker worked out the equations on the fluxes that have to be satisfied. Again, it splits into F terms and D terms. The F terms say that the fluxes have to be without 2,2, and the D terms tell you that G4 wedge J should be 0. It's called flux is supposed to be J primitive. Now note that this is an equality, which means it's the closed condition on the Kähler moduli space. And so in particular, you're not going to get any stability walls out of this. And the heterotic string and the type 2B string, which are supposed to limits of this, the D terms are described by stability conditions. And just to remind you what a stability condition is. So let's think about the heterotic string. You have a bundle V, and you're looking for holomorphic subbundles U inside of V, and your bundle is said to be stable if for every holomorphic subbundle U in V, the notion of the slope, which is degree over the rank, if U is smaller than U of V. So that corresponds to the bundle being stable and therefore satisfying the D-term equations. This involves inequalities. It's a qualitatively different thing from the primitive condition that Becker and Becker write down. So you are never ever going to reproduce that from Becker and Becker. Okay. It's not going to happen. But now that you have a bundle, and in fact, and some of these in the picture, and some of the degrees of bundle are physical using this mechanism that I discussed, you can do some very similar. You can try to write down a condition like this. And that matches with what you see in dual pictures. And in fact, that's one of the things that used to aggravate me to no end. There's a natural Philopolis term that you can write down in F theory or M theory, which actually matches in certain limits with the heterotic string. And there's a candidate Philopolis term, but it's always 0, this condition. What's the point of having a Philopolis term if you're M theory if it's always 0? But with this, you can, if you have a bundle in the picture, well, you can try to use it to define a stability condition. So first of all, I use this notion of the slope that exists in F theory, and then you start looking for subbundles U inside of V. But there's one additional thing that you have to worry about, namely, so when you're studying subbundles U inside of V, what you're worrying about is if V can deform to U plus V mod U. And if that's related by a one-form Gates transformation, then that's not a real decay. So you should not consider those physically distinct. So you want to consider only subbundles U and V, since that this deformation is physically is physically distinct, meaning that it's not just, you can't undo it by this one-form gauge transformation, or in other words, given the formulation you had earlier, when you restrict it to the exceptional locus to a boundary, this deformation should be non-trivial. And you can sort of see how this would match with the heterotic string. Oh, I don't have to talk about it anymore. Yeah, so I'm going to stop at this point. I didn't have much more, so I'm just going to stop. Thank you.
The mode you talked about that exists when there's an effective growth. It can arise when the K3 surface is smooth before it develops a singularity. But your condition, that certain one-form gauge transformation isn't allowed. You only want to impose when the singularity occurs.
No, so it only no, this Friedman-Morgan mode, it only exists when you have an effective curve in the class alpha, which means that the complex structure has been tuned so that you have a singularity, and then you resolve it.
Yeah, the K3. I mean, from the point of physically, the K3 surface is hypercalorimetric.
Yeah.
So that hypercalorimetric might be the resolution of the singularity. When that's the case, you get this mode.
Yeah, so you have to worry about an additional thing there. So Friedman and Morgan were really thinking about F theory.
I see.
And they were completely free to blow up the singularity because it's not a physical mode in F theory. You can blow it up and then you have to take the limit to restrict it like that. If you think of this in the M theory context, basically that mode they discover is the third adjoint field, which I try to shuffle under the rug here. I told you about two adjoint fields. There's actually a third adjoint field in M theory, and it's precisely this blow up mode. And yeah, using the hypercalar structure, right? See that you only get enhanced gauge symmetry when you also shrink that one to zero.
Okay, thanks.
And no more questions before we thank Martin again. I'd like to remind you that you're going to dinner. And send me an email so you know how to make the reservation. Thank you.